Hello. In this video, I would like to share with you ways to use logarithms to solve exponential and logistic equations. It is worth noting that the use of logarithms is usually only necessary to solve for an unknown variable in an exponent. Variables in other positions can be solved using simple algebra. In example 1, we see an initial amount of $2,000 is invested to earn compounded interest. By using the provided equation, we can substitute known values into the appropriate variables of the equation. The unknown variable that remains is time, which is found in the exponent. Therefore, the use of logarithms would be prudent. Personally, I like to solve as much as I can without the use of a calculator, but you can certainly approximate values with decimals if it helps you understand the process. I'll show the decimal technique here and let you consider the more advanced process of avoiding the calculator on your own. First off, we can use a calculator to simplify the interior of the parentheses. At this time, we can divide both sides by 2,000 to begin to isolate t. Now that we have a base value and an exponent, we can use the definition of a logarithm to rewrite this equation. We can use a calculator to evaluate the logarithm. Then divide by 12 to isolate t. So it looks like it would take approximately 9.27 years for the initial $2,000 to double to $4,000 at this rate. In the next example, we consider the law of uninhibited growth and decay. A population of 2,000 mosquitoes grows to 10,000 in an unknown amount of time. It is known that the population grows at 25% per week. Perhaps we need to know the amount of time that passes, since a population of 10,000 mosquitoes warrants some sort of intervention on our part. Let's first replace the known values for variables in the equation. Now let's divide both sides by 2,000. In this case, the base of the exponential is the value e. So I'll use the definition of the natural logarithm to rewrite this exponential. Rather than reaching for the calculator just yet, I will divide both sides of the equation by 0.25. Now I can use the calculator without losing accuracy due to rounding earlier in the process. It appears the population will grow to 10,000 in 6.44 weeks. I would like you to try the next example on your own. Keep in mind that a rate of decay will be represented by a negative number. Pause the video now and resume playback in a moment to check your work. To finish this video, we consider a logistic equation. A logistic equation utilizes an exponential equation in the denominator of a fraction. This affects the behavior of the function growth such that the function values initially grow exponentially, but will level off towards a limiting population. This is sometimes called the carrying capacity. For example, it is impossible for the number of people that have heard a rumor to exceed the population. An exponential equation model will grow beyond the population limit, whereas a logistics equation will not. In this example, a population of 84 students are introduced to a rumor that spreads at a rate of 25%. The origin of the a value is not critical for this lesson. To solve this equation for t, I would initially consider a pair of equivalent fractions and rewrite them using properties of proportions. Now we can continue solving for t without the fractions. Subtract 1 from both sides, then divide by 65.9. Now rewrite the exponential equation as a logarithm and divide by negative 0.25. We have a solution for t now, 16.75 days. Hopefully you found this video helpful. Additionally, I hope you realize the need to be familiar with the definition of logarithms and how they can be used to help solve exponential equations. I suggest you try similar problems on your own and continue practicing these techniques. Good luck.